So yeah, as you can see, they're getting larger. And then it becomes easy to, set how quickly, like I think I have a little bit more of a sloping ramp. I want them to get bigger a little bit quicker. So paste values here, and they'll set any kind of interpolation on that uh, curve that you want. So that's the first thing we need. We got them scaling up. And then we want to set a group. And I'm actually just going to drag this one over. This is the pop group, which is very powerful. It allows you to add points to a group based on a lot of different criteria. So you can set a rule, like an if statement. You can say, once the particles reach a certain position in Y, for instance, add them to a group, or bounds. But what we want is just a random value. And what we want is to add 45% of the particles to a group called burst chance that we'll reference later on. So does that make sense so far?
Yeah, quick question from Philip. We don't care about bubble intersections, correct?
We don't. In fact, when they do intersect, they're
It
all going to
looks
be
cool.
meshed.
Yeah.
Yeah, they'll be meshed together later, and it works totally fine. I think in a situation, Philip, where you're doing close-ups, you may want to use like pop grain or something or pop attract to add some distance between bubbles. But in our case, it's not necessary.
But even if it's a close-up, maybe you do want them to intersect.
Totally. And bearing in mind, this is a fairly stylized effect too.
Mhm.
We're going for something that's somewhat stylized.
Cool.
Yeah. So we don't need a geometry wrangle. We need another pop wrangle. And we'll set our first rule. So like I said, we need to set some rules to add these points to a group that we can then burst. I'm going to color this red. And now the reason I'm coloring these pop wrangles is because the rules that we set on them will also set their color when that rule is made. And the first one is we want to add particles to a group based on their p scale. So the first line is we're going to set a slider to set the threshold, the maximum. And in this case, it's 0.2. So 0.2 will be the max that we want those particles to just be sized in their p scale. And then we have a rule here that says if they exceed that value, then add them to a group called burst group. This is a very handy Vex expression that I use all the time. And if you set add group underscore, after that, this will be the group name. And you can either add points or particles to that group or get rid of them by setting an integer. So in this case, add them to a group called burst group. And also set their color to red. So let's go ahead and play through, and it'll take a few moments for a few of the particles to reach that size, but you'll see it's handy to actually see it visually when it happens. And this is actually the reason this is chugs a little bit is because it is having to load the advection, pyro advection at every time step to add in the velocity. And I could turn that off, but then we won't have any upward motion. So we should start seeing them soon.
The group will not be overwritten per substep. Is that right?
It won't. There we go. So that's the first particle that exceeded a p scale of 0.2. And now it's added to a group called burst group. second one just popped up there. The reason I want this rule too is because I didn't want to have um, huge particles, huge bubbles. This is a way to just say, okay, once these bubbles reach a certain size, just get rid of them and burst them into um, smaller particles. Because we're adding the scale at every frame and it just goes on and on. So first rule is working. And let's add the second one, top wrangle. And we'll turn this yellow because that's the color that we're going to turn these points once that the rule is satisfied. Also, as you recall, we set a group called burst chance. In this one, we only want to work on that group. We don't want this to be applied to all the particles in our simulation. So we will have to move forward in the sim and only reference that group. Because what we're going to do is set a rule to burst those particles based on their position in the y-axis. The idea being that as those particles go up, they're more likely to burst into secondary particles. All right, so first line. Oops, I missed something. Yeah. How's this view for everyone? Is this working? Like, is it visible?
Yep, looks good to me.
All right. Yeah, this is a little bit of a longer next line. So even though I'm calling this min y, min y, min y, max y, these are arbitrary values. I'm really just taking a random number based on the particle's ID and assigning it a value that I can then compare to its position in y. And that'll make sense in a minute. So I just want a minimum value of 8 and a max of 12, because remember, 12 is our boundary anyways. So now all the particles will have a float value, a float variable called burst range in that range at random. And once they have that, you can just use another if statement. And what this does is it just compares that random value to the particle's current position on the y-axis. And if it exceeds that, then it's added to the burst group. And its color is turned to yellow. And this will make sense once we run it forward a little bit here. So you can already see some of those points are turning yellow. They're being added to that group. So if I draw a little diagram here, so starting at 8, you'll see there are no yellow particles below 8 and ending at 12. If you have a particle that has a value that's been given a random value of 8.5, excuse my handwriting, then they're going to turn yellow right about here. And if it has a random value in the range of 10, then it'll wait till it hits this. And that's just a way to randomly add them to this group. So they don't always, they're not all bursting at the same time. It's a controllable range. Does that make sense?
That was awesome. Thank you.
So now we have the particles we want in the group to burst them. So now we can burst them. And that's where this second stream comes in handy. So pop replicate is really fun. It's a very powerful pop node. And you can think of it as a specialized pop source. In fact, when we look at it, you'll see a lot of parameters that are going to look very similar to you. to the pop source. So what we're doing here is we're gonna take this the main stream of our main pop stream here and pipe it into the reference stream of this. What that does is it tells it that any new particles that are being created by the pop replicate will belong to their own stream right here. And then we can merge it back into the main stream. So as you can see, this is operating only on the burst group that we created with these two pop wrangles. And once that this pop replicate is activated, once a point is added to the burst group, it's killed. So the original particle is dead, and there's an impulse count of 200 new particles. I also have another Born group, which again is just so I can color the particles once, not to worry about it updating it every frame. So 200 new particles are created. And then in the shape tab, this is their initial shape. They have a uniform scale of 2, which somewhat matches the sizing of the bubble that they're being spawned from. It's not exact, but it's close enough for our purposes. And then some noise to just make it not a perfect sphere. So it's a little bit randomized. After that, we have the attributes that we want to inherit. In this case, we do want to get CD in case we want to reference back to where those points came from, which of these particles they were born from. Although I'm overriding that with this pop color in this case, but just for ease of use if we needed it. And then of course velocity, because we want that upward velocity. Inheriting velocity, and then there's radial velocity so that they move outward, and some variance on that. That's pretty much it. After that, we are setting a p-scale for those particles, and this is just a ramp to vary the distribution of their sizing, similar to what we did on the input. And then a multiplier, just a global multiplier to change their sizing. Once again, we're using that pop advect by volume, updating their velocity based on that pyro. So you'll see it in every single simulation. And then some additional upward motion. And again, using this expression to smoothly transition from a upward force of 0 to an upward force of 18 at the point where those particles reach 3/4 of their normalized age, 3/4 of their age, using the NH attribute as input. And then some additional noise amplitude just to give it some interest.
So in the beginning of the life, it's 0 force up, but that goes faster, faster, faster as it ages?
Exactly.
Okay.
It smoothly interpolates into that. So I'll draw it out one more time because it's a super handy function. So if we have 0 right here and we're multiplying that to the force, it's going to be 0 at the beginning. And then we're multiplying that by 1 at the end. That's going to now be 18 over a smooth curve with the normalized age as the input. So 18 when it's at 0.75 of that particle's age. And what that does is it allows the points to have some initial velocity outward, and for the pop advect to grab it a little bit, but then they start to hang around like bad guests, and you want to give it some upward motion to get them out of the frame, and so they're not just hanging out. So let me play through that. You can see those particles that we added to those groups are now bursting into secondary particles, and then they'll hang for a moment, and then based on their normalized age, they start to get quite a lot of upward velocity.
We have an interesting question here. So this is an interesting distinction I wanted to point out with the force in your, this is not a wrangle. You've checked on use vexpression. So if you were to put down a regular pop force node, you'd have to click on use vexpression, and then that force, you don't need the at symbol because it's referencing the parameter, right?
That you are totally correct. And thank you for that. Because it is, you can think of this as being a local variable. In fact, if you put down like a pop force,
Yeah.
And you activate vexpressions, if you go here, you can actually get some examples in the little drop down here that'll get you going on some ideas of what you can do with these vexpressions inside of pops. But you can totally do this in a wrangle as well. You could do this with a wrangle,
But you'd
you
have
would
to use the at. So force is still an attribute. It's just in this case, it's also a parameter.
well, it's actually referencing. It's not referencing the force of the overall simulation. It's referencing the force that's being added to. You can force is constantly being added to throughout the simulation. So it's just
Mhm.
referencing this particular force parameter. And if you look at over here, you can see it's force X, force Y, force C
Right.
that will be added to the global force of the simulation.
So we have some more questions here.
Sure.
Do these apply to all the parameters in the node? If so, what's the syntax for ones that are more than one word, which is pulse length?
I'm not sure I exactly follow.
Yeah, this is so Alex, this is a um yeah, exactly. So if you go back to the pop force node,
Yeah.
this is the discussion happening in the chat right now.
Okay.
It's all about the pop force. If we can look at the parameters, yeah.
Sure. Sure. Uh, okay.
So if you hover over the name of, for example, yeah, see, it says force, but even down there, noise is even a better example. I think they're talking about that. If you exactly, and if you hover over any
Oh
of
yeah.
those names, that's how you reference them in the syntax. Yeah,
You're totally correct. And again, you can look at some examples. Amplitude by age.
there you go.
Yeah, amplitude by age here is just using that same expression.
Perfect.
Yeah, it's so yeah.
And then at the end of the day, it all goes to force.
It's added to force. Yes.
Got it.
Um, so yeah. Okay. So that's the main. We're advecting that, adding it back into the mainstream, and then we're advecting it all again. This time updating force. I believe this is updating velocity for the secondary particles, and then advecting the force. So let's see what's next. Oh yeah, and then of course, pop kill here is just again referencing our bounding box, uh, the global domain. That gives us our main bubbles, and go back to our main view here. Camera view. Anything else on that before we step into the next chapters?
I think we're good.
Okay. All right. So let's see. All right. So in the next step here, we want to get rid of the attributes we don't need. Just keep, we're deleting non-selected pop nets tend to output a lot of stuff that we don't need. And then we want to split out the secondary particles from the primary bubbles. So we got a split SOP here based on a stream called burst, which was that stream we created. And we got main burst here, which we can reference later. And then the bubbles, the larger bubbles themselves in this group. And next, and this is kind of fun. Sometimes I find it fun to add to the particles motion after the simulation. And in this case, something that's really fun about bubbles is that they have a little bit of a spiraling. You might be able to see it better in this wireframe. There's just a little bit of a gyrating motion. You can see a wiggle as they rise. And although we could probably simulate that, we could do that in the particle sim. We'll do that post sim just for fun. So what we're going to do is use a sine function. Now, a sine function, without getting into geometry too much, it just it returns a smoothly oscillating value between 1 and -1 based on its input. And most of us are familiar with sine waves. So it's going to do something like this. Oops. I don't know what I did. One more time. The one time I actually drew a nice line. So yeah. Just imagine this camel's hump is actually more rounded. So 1 and -1. And where our input is going to be time. So that will smoothly oscillate between 1 and -1 based on an input of time. And what that gives us is, let me go to a different view here. We're going to add a trail. And first of all, let's just look at the x-axis, because we're using actually a sine and a cosine, but let's start with sine. So all right, so no sine function over time. And then we add it in. You can see we're getting some nice waviness as they're moving through space. And it's fun because time is the input. So the particles that are moving faster will be stretched out, the slower ones. And also setting a few rules in this expression to say, to do a few things, because we're taking time, multiplying it by a frequency. You can see if I move it upward. Since this is not a simulation, we can do this all kind of in real time. So multiplying time by a value will make that the frequency of the sine waves more. And then the amplitude, you just kind of push that too. And so, yeah, it's just a little more real time in terms of, what you're doing. And then the particles will just pick that up and they'll happily take on that motion. And in this case, for this particular effect, seem to work pretty well. I'm also offsetting it by the ID so that they're not all kind of waving at the same. There's a difference in how they're waving. And multiplying it by the particle scale, which just means that larger particles, how was I doing it? Yeah, larger particles will have more of an amplitude. And what was the amplitude I had? I believe it was 1. So yeah, that gives us a sine wave on the x-axis, and the cosine is the same, except that it's at the function returns those that oscillating wave at a 90-degree angle. So if we comment that out, we'll see it's doing the same thing, but this time on the z-axis. And then if you combine those, you get a spiral. So we get kind of smoothly spiraling motion. And those of you who are geometry whizzes, you know all about sine functions and radians. They take radians as input. But for our purposes, it's just a way to get kind of smoothly repeating values used all the time in expressions. Anything on that?
Looks awesome. I think we're okay.
Okay. All right. Next. Okay, copy to points is the next thing. So these are all, this is all great and good, but we don't want to, these don't look like bubbles. They're too spherical. What we're going to do is we're going to kind of simulate the look of bubbles by copying some geometry to these points and inheriting some attributes. So let me, I think we're making our way through this, right? Is this all making sense to everyone?
Yeah. We did have a question about chops, if what your thoughts are on that, but we could save that to the end because it sounds like it could be a top discussion that we could have.
Oh yeah, and a lot of these things can be done with chops.
Yeah.
If you're talking about sine waves and things
Right.
like that, or wiggle, yeah,
Mm.
you can do all that post sim and do a lot of fun stuff by all means.
Yeah, everybody right click on any parameter and use motion effects and see what happens.
Absolutely, yeah. All right, so yeah, at this next stage, we're going to copy some geometry to create the bubbles that we just did. And first of all, we're going to be deforming these bubbles. Let me start by just also bringing over the awesome geometry of these bubbles. You'll see it's how amazing this is.